Kia ora koutou. In this video, I'm going to go through some of the permutations and combinations proofs that we've done in Scholarship Calc this week. This is both for people who weren't there on Thursday morning and also people who might have missed the Saturday session and wanted to catch up. So there'll probably be about 3 videos and they crank up in order of difficulty. I'm not going to do any of the basic ones about what a combination or a permutation is, so there are no questions in here about choose 10 people out of 20 to go on a committee and stuff like that. Instead, what I'm focusing on is the proofs about things to do with the binomial theorem, where we have to use the definition often of combinations. So just starting off, the binomial theorem tells me this. If I've got x plus y to the power of n, then I can do that expansion as follows. And I've done other videos that look at this. If this is the first time you're seeing this, if you go and find either 12 MCA or 13 MCA and search up Schol and binomial theorem, you should get some stuff. All right, so I'll do a couple of examples of this before we get going with these harder questions. If you've got, for example, x plus y to the power of 4, then these numbers are going to come out of the 4th row of Pascal's triangle. And that's what a lot of today's questions were all about. Right, so 4 choose 0 times x to the power of 4, y to the power of 0, plus 4 choose 1, x cubed y, plus 4 choose 2, x squared y squared, plus 4 choose 3, x times y cubed, plus 4 choose 4 times y to the power of 4. And when I clean that up, I get x to the power of 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the power of 4. So you can see those coefficients are matching up to Pascal's triangle. And to get to the next row in Pascal's triangle, I take the 2 entries above it and add them together. What else did I want to say? So this works for positive integers. It also kind of works for negative and fractional powers, but we're definitely not going to see that in Scholarship Calc. You do see that in A level. So if you're watching my A level videos on this, you'll see lots of examples of things like, I don't know, 1 over this, and you have to expand this, right? So this is quite different. This is where I'd write this as 1 plus x to the negative 1/2, and this turns out to go on forever. And in some situations, it will reach a stable limit. We say that it converges. We're not going to do any of that today. What we want to think about is these Pascal's triangle numbers. What are they? Well, they're combinations. And a combination, if we have n choose r, so just some notation first of all, what we're asking is how many ways to choose r objects from n when we don't care about the order of those objects. All right, but we don't have to use this meaning very much in the scholarship questions that I'm going to do now. Instead, what we're going to be using over and over is what exactly is the definition of one of these weirdo combination things. Well, it's n factorial over r factorial times n minus r factorial. For example, if we've got 5 choose 3, which we can write as 5, 3 in the brackets like that. So we say that as 5C3 or 5 choose 3, or some people would say 5 combination 3. Then what we've got here is how many ways to choose 3 things out of 5. So we've got 5 ways to choose the first thing, and then we've got 4 things left, and then we've got 3 things left. But because we don't care about the order, then if I have A, B, or C, that's the same as having C, B, or A, or B, A, C, or B, C, A, or A, C, B, or C, A, B. So for every set of 3 letters, there are 6 doubles. So we have to divide this answer by 6. And if you look at what we've got in there, that is exactly the same as 5 factorial divided by 2 factorial divided by 3 factorial. So this bit here is my permutation, where I do care about the order. And I'll just change pen colour. This 3 factorial is where I'm getting rid of the double ups, because for a combination the order is irrelevant. So what that leaves us with, though, is that this is really important for these two problems. The first question we're going to look at here finally is to use the binomial theorem to prove that 2 to the power of n is equal to all of that stuff. But whenever you're doing a binomial theorem thing like this, there will be a link to Pascal's triangle. So what we're saying here is that if we look at the nth row of Pascal's triangle and we add the entries up, we're going to get 2 to the power of n. And this is something that most students haven't ever played around with. So let's just have a look at how it goes now. Here's Pascal's triangle. So this is the 4th row, so 4C0, 4C1, and so on, out to 4C4. And you can see that if you add those up, you get 1 and 4 is 5, 5 and 10, 15, you get 16, and 16 is 2 to the power of 4. Look at the next row. Do we get 32? Yes, we do. Right, so 1 and 5 is 6, 6 and 20, 26, 32, and that's 2 to the power of 5. So that's pretty cool, and we're going to prove how it works now. So 2 to the power of n, to apply the binomial theorem, I need to say, well, it's something plus something to the power of n. So 2 is 1 plus 1. And once we've got that, we are off and racing, because x plus y to the n is equal to n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the 1, and so on, all the way out to n choose n, x to the 0, y to the n. But when we start substituting that in, so we've got 1 plus 1 to the power of n, well, 1 to the power of n is just 1, and 1 to the power of anything is 1, so we're done. So we're left with n choose 0 plus n choose 1, and so on, all the way out to n choose n. Now what this means for the rest of these questions is that whenever you see a 2 to the power of n in a question, it's really useful to think about it as the sum of all of the entries in row n of Pascal's triangle. And that's what we're going to do in the next question. So the next question is another one where we're going to be applying the definition of a combination. This is definitely a step up. Part A, I think, is warm-up scholarship level. Part B is scholarship level, especially like if you're just seeing this for the first time. We'll just get rid of all of this and have a little bit of room. Hopefully you just forward through that 10 seconds. So when I look at this, before I kind of dive into the proof, I might just work on expanding that 2 to the n minus 1 and see what we get first. So 2 to the n minus 1 is the n minus 1th row of Pascal's triangle. And from the result we had up above, we get this. I'm going to write a few terms out, and then at the other end, we'll just write out the last one. I'm going to apply the definition of a combination now, and I want to end up with n times 2 to the n minus 1, so I'm going to start working that through now. So the left-hand side gives me n times 2 to the n minus 1, which is n times, right, off we go, n minus 1 factorial over 0 factorial, n minus 1 minus 0 factorial, plus n times n minus 1 factorial over 1 factorial, n minus 1 minus 1 factorial. Remember, in the factorial, in the combination, the denominator is going to have this factorial, and then it's going to have this take away this factorial. So the next term will be n times n minus 1 factorial over 2 factorial n minus 1 minus 2 factorial plus, oops, that should be not a times, that should definitely not be a times, it should be a plus. And then let's do our last term, it'll be n times n minus 1 factorial over n minus 1 factorial 0 factorial. Now look, I should know by now that this is equal to 1 and this is equal to 1 as well. But I'm not going to do it quite yet just because of the format of the right-hand side where I'm trying to get to. So putting that together is going to get me just about where I want to be. Remember that n times n minus 1 factorial can be put back together again to give me n factorial. So I've got n factorial over 0 factorial n minus 1 factorial plus n times n minus 1 factorial. Whoops, so I want to put that back together. Right, so looking at that, I've got n factorial over 1 factorial n minus 2 factorial plus n factorial over 2 factorial n minus 3 factorial plus n factorial over n minus 1 factorial 0 factorial. And if we look at where we're trying to get to, we want to end up with n choose 1 here, n choose 2 here, n choose 3 here, and so on. So focus on that when you're working on the problem, and we're going to try and force those in now. So look at where we've got to. Just get rid of the mess from the last question. We're trying to get to n choose 1 and then n choose 2. This is just about n choose 2, except that I've got a 1 here instead of a 2. And this one here is just about n choose 3, but I've got a 2 here. And the same thing here. This is nearly n choose 1 here, but I've got a 0 factorial here. Now, as it turns out, this is actually fine. 0 factorial is equal to 1 factorial. Both of those are equal to 1. That was a kind of basic fact that I taught everyone in class, but I think I forgot to say it in this video. So in this one here, we can write straight away n factorial over 1 factorial n minus 1 factorial. And if I want to have this be a 2, what do I have to do? Well, I'll times in by 2 over 2 times 1 factorial times n minus 2 factorial. And here, if I want to have 3 factorial, I can times by 3 over 3. And so on. And then in this last one, if I times by n over n, I'll get n factorial over, what will I get there? N factorial times n over n factorial 0 factorial. Putting all of that together gives me n choose 1 plus, here's my n choose 2 factorial. And then here is my 3 factorial, and my n minus 3 factorial, and my n factorial. And lastly, I've got n factorial here. Sorry, just n here. And then n choose n here. And we're done. So there you go. I'm getting a bit too tired to do the rest of these questions tonight, so I'll try and get onto them either tomorrow or Monday. If you've got any questions or comments on this, just send me an email or leave a comment underneath. Thanks for watching.